Unit 6, Video Lecture 4, Determining Empirical and Molecular Formulas. Determining empirical formula. In our last video lecture, we looked at how to determine the percent composition of different elements and how they existed within a compound. Well, when we're going to determine the empirical formula, we're going to be working with the percent composition, and we're going to convert the percent composition to mass. After we convert to mass, we're going to need to use our molar mass and figure out the number of moles of each of our substances. What we're then going to do is we're going to compare and then divide by the smallest number of moles. And then this will eventually give us an empirical formula. So let's take a look. The percent composition of an oxide of sulfur is 40.05% sulfur and 59.95% oxygen. Determine the empirical formula. Well, we're given 40.05% of sulfur and 59.95% of oxygen. For our map, what we're going to do is we're going to start with our percent composition, and we're going to change our percent composition into mass. Once we've figured out the mass of our substances, we're going to convert that to the number of moles that are present. We can then divide by the smallest number of moles. And then finally, that ratio is going to help us to determine our empirical formula. So, to convert from percent composition to mass, we're going to simply take our percent. So for sulfur, we're going to take 40.05%. And we're going to drop the percent sign and put grams. Because we're going to assume that we have 100 grams of the substance. Since we're not told otherwise, we can just assume that we have 100 grams of the substance. So if we do that, if we assume 100 grams of the substance, and we have 40.05%, well, what number divided by 100 will give us 40.05%? 40.05. So for oxygen, we'll take 59.95 grams of oxygen. Now that we have the mass, we're going to convert to the number of moles. So to do this, we do a mole conversion. If you don't remember the molar mass of sulfur, we'll have to look it up. We find sulfur and we see that the mass is 32.07. So the molar mass of sulfur is 32.07 grams in 1 mole. Well, we want grams of sulfur to cancel out, so we'll put our 32.07 grams on the bottom and our 1 mole of sulfur on the top. So we'll do the same thing for oxygen, knowing that oxygen's molar mass is 16.00 grams per mole. So 16.00 grams of oxygen goes on the bottom, 1 mole of oxygen goes on the top. So now we calculate the number of moles that are present. So we take 40.05 divided by 32.07, and we get 1.2488. Rounded to 4 significant figures, we have 1.249 moles of sulfur. We then take our 59.95 grams of oxygen divided by 16, and we get 3.7468. Well, rounding again to 4 significant figures, we have 3.747 moles of oxygen. So we've taken our percent composition and converted it to mass. Converted our mass to moles, and our next step is to divide by the smallest number of moles. Well, in this case, 1.249 is the smallest number of moles. So we're going to divide both of these by 1.249. So 1.249 divided by 1.249 is 1. So we have 1 mole of sulfur, and 3.747 divided by 1.249 is 3. So we have 3 moles of oxygen. So our empirical formula is S1O3. Let's determine the empirical formula for methyl acetate, which has the following composition: 48.64% carbon, 8.16% hydrogen, and 43.20% oxygen. Well, we're given our percent compositions. We're given 48.64% carbon, 8.16% hydrogen, and 43.20% oxygen. We want our empirical formula. So again, we're going to start with percent composition and convert to mass. We're then going to take our mass and determine the number of moles that we have. We'll then divide by the smallest number of moles, and that ratio will give us our empirical formula. So we'll take 48.64% carbon, and again, remember, we're going to assume that we have 100 grams, so all we have to do is drop the percentage sign and put a grams. We have 8.16 grams of hydrogen and 43.20 grams of oxygen. So we've taken our percent composition and we've figured out our mass. Now we're going to convert to moles. So we're going to use our molar mass. The molar mass of carbon is 12.01 grams equals 1 mole. Since I want grams to cancel out, I'll take 12.01 grams and put it on the bottom, 1 mole, and put it on the top. This gives me 48.64 divided by 12.01. I have 4.050 moles of carbon. The molar mass of hydrogen is 1.01 grams equals 1 mole. So since I want grams to cancel out, I'll put 1.01 grams on the bottom and 1 mole of hydrogen on the top. So 8.16 divided by 1.01 says that I have 8.07, rounded significantly, 8.08 moles of hydrogen. The molar mass of oxygen is 16.00 grams equals 1 mole. So I put my 16.00 grams of oxygen on the bottom, my 1 mole of oxygen on the top. 43.20 divided by 16.00 is 2.700 moles of oxygen. Well, 2.700 moles of oxygen is our smallest, so we're going to divide each of these by 2.700. Well, 2.700 divided by 2.70 is 1. 8.08 divided by 2.700, we get 2.99. So we'll consider that close enough to 3. And 4.05 divided by 2.700 is 1.5. Well, here's an issue. We have 1.5. We were able to round 2.99 to 3 because this was really close. However, our 1.5 isn't as close as 2.99. So what we're going to do is we'll take our 1.5 moles of carbon, our 3 moles of oxygen, or 3 moles of hydrogen, and our 1 mole of oxygen, And to get rid of this percent, we're going to multiply by 2. So this gives me 3, 6, 2. So my compound will have 3 moles of carbon, 6 moles of hydrogen, and 2 moles of oxygen. Our empirical formula is C3H6O2. Let's determine the empirical formula for a compound that's made up of 75 grams of carbon and 25 grams of oxygen. Well, we're given 75 grams of carbon and 25 grams of oxygen, and we want the empirical formula. So our steps are going to be the same, except we are not starting on percent composition, so we can get rid of that. We're going to start right on mass. So we take our 75.0 grams of carbon and our 25.0 grams of oxygen. Our carbon has a molar mass of 12.01 grams in 1 mole of carbon, and 1 mole of oxygen has a mass of 16.00 grams. So 75.0 divided by 12.01 is 6.24 moles of carbon, and 25 divided by 16 gives us 1.56 moles of oxygen. So we've gotten our mass, we've converted to moles, now we'll divide by the smallest number. Well, we'll divide them both by 1.56, so 6.24 divided by 1.56, and we get 4 moles of carbon and 1 mole of oxygen. So, given this, our formula would be C4O. You can click on the above link to do more practice problems on percent composition to empirical formula, or you can keep watching as we move on to molecular formula. It's possible to determine the molecular formula once we've determined the empirical formula. And for that, we're simply going to use the equation of molar mass divided by empirical mass. So we're going to need to be able to recall this formula from memory. Molar mass is the mass of 1 mole of the substance, and the empirical mass is the mass of the empirical formula. So if the empirical formula for a substance is HO, well, the molar mass would be 1.01 plus 16, so the empirical formula would be 17.01 grams per mole. So let's practice. The molar mass of acetylene is 26.04 grams per mole. The empirical formula is CH. What's the molecular formula? Well, we're given that the empirical formula is CH, and we're given that the molar mass is 26.04 grams per mole. We want the molecular formula. So to do this, we just can go from empirical formula to molecular formula by taking the molar mass and dividing it by the empirical mass. So the molar mass is 26.04 grams per mole. We divide that by the empirical mass. The empirical mass, carbon, has a mass of 12.01. Hydrogen has a mass of 1.01. So our empirical mass is 13.02 grams per mole. 26.04 divided by 13.02 gives us 2. This 2 tells us how much bigger our molecule is than our empirical. So our final step is to take our empirical formula, CH, and multiply our ratio by 2. So this means that our molecular formula is C2H2. The experimentally determined molar mass of benzene is 78.12 grams per mole. The empirical formula is CH. So what's the molecular formula of benzene? Well, we're given the empirical formula at CH, and we're given the molar mass at 78.12. We want the molecular formula. So again, our map will go from empirical formula to molecular formula, and we do that by taking the molar mass and dividing it by the empirical mass. So our molar mass is 78.12, and our empirical mass we'll still figure out the same way. Carbon has a mass of 12.01, hydrogen has a mass of 1.01, so that gives us an empirical mass of 13.02. So 78.12 divided by 13.02 gives us a 6. So that means that the benzene molecule is 6 times as large as our formula CH. So CH times 6 means that we have 6 carbons and 6 hydrogens. So benzene's molecular formula is C6H6. In this problem, we're given our percent composition of 40.68% carbon, 5.08% hydrogen, and 54.24% oxygen. We're also given the molar mass at 118.1 grams per mole. In order to determine the molecular formula, we're going to have to determine the empirical formula first. So the first thing that we're going to have to do is take our percent composition and figure out the mass. Once we figure out the mass, we can determine the number of moles. We'll divide by the smallest number of moles. That'll give us the empirical formula from which we can calculate the molecular formula. To go from percent composition to mass, we simply take our percents and make them grams. So 40.7 grams of carbon, 5.08 grams of hydrogen, and 54.2% oxygen. Our molar mass of carbon is 12.01 grams per 1 mole. Our molar mass of hydrogen is 1.01 grams per mole. And our molar mass of oxygen is 16.00 grams per 1 mole. So we get 40.7 divided by 12.01 is 3.39 moles of carbon, 5.03 moles of hydrogen, and 3.39 moles of oxygen. Well, we take each of these and we divide it by 3.39. It's the smallest number of moles. And we get 1, but here we get 1.5. We've got that pesky decimal again. So to take care of that, we're going to multiply all of our numbers by 2. To do that, we get a ratio of 2 moles of carbon to 3 moles of hydrogen to 2 moles of oxygen. So our empirical formula is C2H3O2. So now that we have our empirical formula, we can determine our molecular formula. And we do that by taking our molar mass and dividing it by our empirical mass. So our molar mass is 118.1, and our empirical mass, C2H3O2, we have 2 carbons, 3 hydrogens, and 2 oxygens, giving us an empirical mass of 59.05. So 118.1 divided by 59.05 is 2. So our molecular formula is twice as big as our empirical formula. So we take our empirical formula and multiply it by 2. That means that we have 4 carbons, 6 hydrogens, and 4 oxygens. This is the end of our video lecture. You can stop it here and begin your practice problems, or you can continue on for additional practice. Additional empirical formula practice. Determine the empirical formula of a compound that's made up of 52.7% potassium and 47.3% chlorine. Well, we're given 52.7% of potassium and 47.3% of chlorine. So our map is going to be percent composition to mass, mass to moles. We'll divide by the smallest number of moles, and that ratio will give us our empirical formula. So 52.7 grams of potassium and 47.3 grams of chlorine. If we don't remember our molar masses, we'll have to look them up. Potassium has a mass of 39.10, so 39.10 grams of potassium in 1 mole. And chlorine, 1 mole of chlorine, has a mass of 35.45 grams. This means that we have 1.35 moles of potassium, and we have 1.33 moles of chlorine. So we divide by 1.33, and we get just about 1 and 1. So this means that our empirical formula has a ratio of 1 mole of potassium to 1 mole of chlorine. So our empirical formula is KCl. Determine the empirical formula of a compound that's made up of 22.1% aluminum, 25.4% phosphorus, and 52.5% oxygen. Well, we're given our percent compositions, and we want our empirical formula. So our empirical formula, we'll starting with our percents, and we'll go to our mass. From mass, we'll determine the number of moles. Once we have the number of moles, we'll divide by the smallest number of moles, and that ratio would then give us our empirical formula. So 22.1 grams of aluminum, 25.4 grams of phosphorus, and 52.5 grams of oxygen. If we don't remember our molar masses, let's go to the periodic table and look them up. Aluminum has a molar mass of 26.98. Phosphorus has a molar mass of 30.97. And oxygen has a molar mass of 16.00. So, 1 mole of aluminum has a mass of 26.98 grams. 1 mole of phosphorus has a mass of 30.97 grams. And 1 mole of oxygen has a mass of 16.00 grams. When we take 22.1 divided by 26.98, we see that there is 0.819 moles of aluminum. When we take 25.4 divided by 30.97, we see that there is 0.820 moles of phosphorus. And when we take 52.5 divided by 16, we see that there are 3.28 moles of oxygen. So we divide by the smallest number of moles, which is 0.819, and we get 1, 1, and 3.28 divided by 0.819, we get 4. So 1 mole of aluminum and 1 mole of phosphorus and 1 mole of oxygen, and 4 moles of oxygen. So that means that our empirical formula is AlPO4. You can click the link at the end. You can click the link above to go back to our video lecture, or you can continue on and we'll work some practice problems when we're converting from molecular formula. Additional molecular formula practice. The empirical formula of a compound is CH2. Its molecular mass is 70, let's make this 70 grams per mole. What is a molecular formula? Well, we're given that the empirical formula is CH2, and we know that the molar mass is 70 grams per mole. We want our molecular formula. So to do this, we take our molar mass and divide it by our empirical mass. Our molar mass is 70 grams per mole. Our empirical formula is CH2. Carbon has a mass of 12.01, and there's 2 hydrogens. So 12.01 plus 2 times 1.01 gives us a total mass of 14.03. So 70 divided by 14.03 gives us 5. So in this case, our compound is 5 times as big. And multiply by 5, which means that we have 5 carbons and 10 hydrogens.